Hello. In this video lecture, I will be covering Chapter 5, Module 5, Applications of Newton's Laws. The chapter basically is a continuation of the previous chapter, Chapter 4, where we covered the three laws of Newton, Newton's first law, second law, and third law. The first law is the law of inertia. The second law is a mathematical law, F equals ma. And then the third law is the law of action-reaction, which is for every action there is a reaction. The concentration here is going to be on the second law, F equals ma. Pretty much almost 90% of the problem that we're going to be dealing with in this chapter. So there is really no topic to cover or no new topic to cover. It's all basically just, we're just going to be doing problems from examples from the chapter, the examples that are solved. And I will do maybe 2-3 problems from the homework problems. Okay. So let's start. So when we say application of Newton's law, we are really talking about the Newton's second law, which is said that the sum of the forces on an object is equal to the kinetic reaction, ma. Okay. Where A here, of course, is the acceleration, and the sum of the forces are basically all the forces on that object. A simple example of that is, the simplest of all is, say, imagine you have a book resting on the table. Here is the surface of the table right here, and here is the book. And we ask the question, what are the forces on the book? The forces here are two. One is the weight of the book, what I call mg, or W your book would call it, mg, mass times g, the acceleration due to gravity. And then you have, from the third law says for every action there is a reaction, so there is a reaction to that weight, and that reaction we refer to it as the normal vector, and it is the normal big N, like that. Whoops, I'm at the edge of the screen, so I'll put the N here. There we go. Okay? So when we apply Newton's second law, the one that you see above here, the sum of the forces is equal to, well, the book is not moving, not in motion, and therefore the acceleration is 0, so we say it's equal to 0, okay? So if I put a vector on it, so this is the sum of the vector forces is equal to the null vector, the 0 vector, you see what I'm saying? This equation, we refer to it as, it's a statement of what we call the equilibrium state, the equilibrium state. Equilibrium means, the word equilibrium means all the forces on the object add up to 0, okay? And because they add up to 0, that means there is no kinetic reaction, ma. The system is not going to move. An example of that, just like I said, the book resting on the table, or maybe say a chandelier hanging from the ceiling. The chandelier is not moving, and what are the sum of the forces on the chandelier? Let's say here I have a ceiling here, and you have the chain right here, and here is the chandelier. I'm just going to symbolize it with a block or a box like that. So what are the forces on it? Again, we say that there is the weight of the chandelier, mg. There is no normal because the chandelier is, remember, normal happen only when an object is pressing against a surface. You see what I'm saying? There is no surface here, so the normal is not there, but we have a tension, T. Like that, big T. And always tension always come out of the body. Okay, so if you're wondering which direction the tension, it's always out of the body. You get that? So it is out, so it will be in the up direction like that because the body is below it. Okay, so here again it is an equilibrium because the sum of the forces here add up to 0, and we have two forces. Of course, specifically in the y direction, I have my coordinates here. Let's say x and y. As you can see here, there are no forces in the x direction. They're all in the y direction. So if I would add them up together, up means positive, down negative, so it's going to be T minus mg, and that's equal to 0. That tells me that the tension is equal to mg. Just like the action-reaction law. For every action there is a reaction. Equal in magnitude and opposite in direction. As you can see, they are opposite in direction here, but they are equal in magnitude, okay? The same thing applies for the book sitting on the table like that. So I apply my, if I put my datum, X and Y, here is the X and Y right there. And as you can see, the forces, those two forces, the normal and the weight, are in the Y direction. So if I apply sigma F equals 0, again, 0, Y0 is because, let me just fix that. Y0 is because the system is not moving, right? It's not accelerating or anything like that. So here we have the normal plus the normal, because it is up, minus the mg equal to 0, and therefore the normal is equal to mg, and we arrive basically at the same formula as the chandelier. You see what I'm saying? So that's basically the meaning of equilibrium. There is more to it than that. We will cover this in a later chapter, but for now, that's basically how you do that. Now, when you deal with a system where the sum of the forces is equal to 0, we call that equilibrium, and we say that the system is in a static situation. That's another word, okay? So we have a equilibrium state, or we have static, okay? Static, which is versus dynamic. Excuse me. Dynamic means it's in motion. It's an accelerated motion, for example, where a static situation means it is, I believe the Greek or the Latin word status, which means not moving, constant. You see what I'm saying? So that's the meaning of it. So those are two words that you want to be familiar with, equilibrium and static, and they both have the same kind of, pretty much the same meaning, okay? All right. One more thing before I start doing some examples from the book. So let me go back to that equilibrium state. Sigma F equals ma. I'm sorry, I want to do it 0. Sigma F equals 0, which is the static or equilibrium state, right? Because there is a possibility that those forces here are distributed either in the X direction or in the Y direction. So this equation really, if I put a vector notation on it, this equation really has two components. One, sum of the forces in the X direction equals 0, and sum of the forces in the Y direction equals 0. And I always saw when I deal with a problem, especially a two-dimensional problem, which we're going to do in a second, you want to split this equation into two components, the X component and the Y component, okay? So I'm going to concentrate first on a couple of problems from the book on the static situation where we have to split it into components, and then later on we're going to deal with problems where the system actually is in accelerated motion. So in other words, it's sigma F equals ma. You see what I'm saying? So let's do that. I'm going to start with problem number 2 from the book. Let me go do it in my, well, let me show it to you here. I think, let me find it in the book and I'll tell you what page is it. 5.2 on page 124. Here it is right here. Let me make it bigger. It's too big, but that's all right. There we go. So what you're looking at here, this situation right here. So you have an engine of a car is hung from 3 chains like that. You see that? And this chain is with 60 degrees with respect to the horizontal. And there we go. So anyway, let's read the problem together. Let's start from here. It says, as shown in figure 5.2, a car engine with a weight W, okay, hangs from a chain that is linked at point O, right there, to 2 other chains. One fastened to the ceiling and the other to the wall. As you can see here, this is to the ceiling, this is to the wall. Find the tension in each of the 3 chains, assuming that the weight is given and the weights of the chain themselves are negligible. So we're going to neglect the weight of the chain itself. Okay, we'll assume they are too small compared to the engine or something like that. So we're just going to ignore them. All right. So he wants to know the tension in those 3 chains: T1, T2, and T3. Okay. So watch how I do this problem. I'll do it my own version. number, what is it, 5.2. So first thing you need to do, always, you need to draw the free body diagram. Honestly, you couldn't do the problem without a free body diagram. So it really helps you put in what is the equation. So anyway, so I'm going to put, here is the ceiling, here is the wall, and again, so we have this one chain that looks like, first, let me draw that. This is where it is, the ring, whatever it's called, and then I have, here is one chain, here is the other, and there is another one. Let me make it bigger. Here is the other one here, and then there is the engine. We're just going to turn it into a block like that, okay? And this is 60 degrees right here, and this is T3, this is T2, and this is T1 right here. And then, of course, we have the weight. He calls it W. Again, I like to call it mg. Anyway, so what are the forces on it? How do we do that? The best way to do it is you start from the dot right there. What did he call it? I forgot what he called, the knot or something. He called it ceiling the other to the wall, linked. Okay, link at point O. He just called it link. Okay, we'll call it a link. So we have that link. So here is the link. Let me show you how we draw the FBD, the free body diagram. So here is the link right here. Okay. So what I have, remember, tension always come out of the body. Okay, keep that in mind. Write it down. Okay. Tension always come out of the body. In other words, if I'm going to draw the tension, you're not going to draw it like that. Okay? That's into the body. It always come out of the body. This is just a little hint for you. So T3 is going to look something like that. T2, again, out of the body. Okay? And then I have T1 out of the body like that. There we go. You see what I'm saying? There we go. Okay. Now the angle, he said the angle here is 60 degrees. So it's basically right here. Is that okay? I'm going to make it look better for me. Okay. Now, as you can see, this is a two-dimensional problem. In other words, I have some these are all forces. Okay. I could have called them F rather than T, but T for tension are the same. So I have a two-dimensional problem. What that means is that I have some forces on the y-axis. This is on the x-axis, and this is kind of in between, right? So in other words, the T3 have to be resolved into components, x component and y component. You get that? T2, it's only on the x component, so I don't need to do anything with it. Ty is the y component. I don't need to do with it anything with it. Okay. So what I'm going to do, let me change the color. Maybe that will be help you visualize that. I like pink, right? You like pink? All right. So T3 in this case, it has two components. The x component is going to look like that, and that's going to be T3 cosine 60, and then another one like that, and that will be T3 sine 60. Once I get those components, you can completely disregard the original T3. You see what I'm saying? In other words, those two components have replaced the original, so this resultant. So totally ignore that T3 now, because those two are the one that we're going to be working with. All right, let me go back to black color. So now I used my equilibrium equation, since obviously the engine here is not in motion, so this is in a static situation or equilibrium. So therefore my equation of motion is going to be sigma F equals 0. And of course I have two of them. Sigma F in the x direction equals 0. And I'll make a little space here. Sigma F in the y direction is also equal to 0. Okay? So what are the forces in the x direction? Well, I get the T2 and the T3 cosine. The T3 cosine going to the right makes it positive. This one to the left makes it negative. So I'm just going to add them up together vectorially there. So it's going to be minus T2 plus T3 cosine 60 equals 0. Done. Okay? That's it. Let me box it. I'll come back to it in a minute. Now, when it comes to Ty, I have two as well. I have T3 sine 60 and T1. You see that? Remember, you may say, well, what about the weight? Well, the weight is not in the knot. The weight is not in this link right here. Okay? I'll come back to the weight in a second. I'm only asking, what are the forces coming out of the knot or this link? You see what I'm saying? So the weight is way down there. Okay, later on you'll discover that T1 and the weight are equal, but that's for in a minute. Okay, so basically I'm asking the question. This is very important. A lot of students get confused. Well, what about the weight? I should include the weight there. No, you don't include the weight, because I'm looking at this knot right here, and the weight is way down there. Okay, so I'm only asking what other forces are coming out of the knot by itself. All right, so that's why I have those vectors. So anyway, so for f sub y, that's going to be, again, up means positive, down means negative. So that means I have t sub 3 sine 60 minus t1 equals 0. And there we go, I have another equation. Am I done with the problem? Not exactly. I mean, unfortunately, he didn't give us any numbers, so we're not going to get any numbers out of that. But anyway, now, I want to solve for T1, T3, T2, and T3 in terms of the weight, okay? Now, here is what I do. So this is my first free body diagram, okay? This is my first one right here. Now, here is the second one. The second one is basically the weight, the engine. So here is the engine. Now I ask the question, what are the forces on the engine? Well, obviously I have the weight. We'll call it W for now, because he didn't give us any numbers. Excuse me. All right. And what else? Well, the weight is attached to this chain, and this chain is T1, right? So remember, tension is always what? Coming out of the body. Watch. Out of the body. See that? See the difference between this T1 and this T1? They're equal. But remember, it's always coming out of the body. So you're not going to draw it downward. It's always out of the body. So I have that, and that's it. Those are the only two forces that I have on the engine. Got that? So now I have my own equation here. I'm just going to use my own sigma F equals 0 for the engine itself by itself. Okay? So as you can see here, there is no x component. So I can ignore sigma fx equals 0. I'm only going to be using sigma fy equals 0 for this one. So let me write it down here on the side. Sigma fy equals 0, right? And so I have T1 minus W equals 0, and T1 is equal to W. Okay, that's interesting. Here we go. I solved this one. So it says here that T1 is equal to the weight. I hope you're not surprised by that. It's very similar to the chandelier problem, the one I just done. Okay. So anyway, there we go. He said, T1 is equal to the weight. Okay, now, remember, he said, what is T2, T3, and T1? I found T1, the weight. Okay, we can put a number for the weight. Let's say 50 Newton. I can just plug in 50 Newton, become T1 is equal to 50 Newton. You're done. So anyway, we'll just call it W. All right. Now, let me call those equation 1 and equation 2. Let's come to equation 1. Let's go to equation 2. Because it contains T1. And what is T1? Well, T1 is W. Okay? And so I can solve for T3 in terms of the weight. You see what I'm saying? So I know that sine 60 is 0.866. I always memorized it. So this is, so the equation 2 becomes 0.866 T3 minus W equals 0. Is that right? So therefore, I can do that in one shot. T3 is equal to W over 0.866. And I just need to solve for that. I just want to, says what is 1 divided by, I'm using my calculator here. So 1 divided by 0.866, answer 1.15. So therefore, T3 is equal to 1.15 W. There we go. I have solved for the tension. T3, that is. Okay? Now let me come back. Since I know T3 and T1, I know both of them. So I can just go here, plug in T3, and solve for T2, and I'm done. Done with the problem. He said find the tensions. There we go. So now I go back to 1. 1 says, right there, minus T2 plus T3. What's cosine 60? 0.5 equals 0. Now I just need to do the simple algebra. T3 is equal to 1.15 right there. So therefore, minus T2 plus 1.15 times 0.5 equals 0, and therefore T2 is equal to, again, use my calculator again, and so I have here 0.5 times 1.15, answer 0.75, 0.58 roughly, W. I think I forgot, sorry, I forgot to put the W in there. There should be a W there, right guys? Should I put a W there? Let me just, I'll just put it here. How about that? Equals 0. And there we go. So I have the tension T2 is equal to 0.58. You got that? And that's it. Let's go back to the question very quickly. He says, find the tension in each of the three chains, assuming that W is given, and so on. Okay? So there we go. So we have the answer. Okay? Okay, good. Next problem. I want to do problem number 5.3. This one is a little toughy. 5.3. Next page. Right there. So what you have here is the you have a tow truck, for example, and the tow truck is lifting the car, is pulling the car, but the car is at rest. So in other words, it's not moving. It's not here. Let's read the problem. Start from here. It says a car with a weight of 1.76 times 10 to the 4 Newton rests. So the word rest means what? There is no kinetic reaction, no zero acceleration. Sigma F equals 0, basically. Sigma F equals 0. Rest on a ramp of a trailer. The car's brakes and transmission lock are released. Only the cable prevents the car from rolling backward, blah, blah, blah. Okay. The ramp makes an angle of 26. This alpha right there. This is the angle 26 degrees with the horizontal. Find the tension. So you get this chain. You see that chain right there? He said find the tension in the cable and the force with which the ramp pushes the car's tires. Okay? Not terribly simple. But before I do this problem, I need to solve for you something called the inclined plane problem. This is a very, very important problem in physics. I need to solve that for you before I do this problem. So pay attention to it. You're going to see the inclined plane problem many, many, many times in this semester. Okay, the inclined plane problem. All right, what does that mean? Okay, imagine you have an inclined plane. All right, here is an inclined plane. Let's say a slide in a playground. You know, when you were a kid, you went to the slide and you would slide down. So here it is. So you're sliding down. But well, let's ignore the motion itself. Let's say there is an inclined plane like that, and there is a block, you know, whatever it is, a child or a block of a book or a block of wood, whatever it is, okay? You have an angle theta here, okay? What I'm concerned about here is what are the forces on a body sitting on an incline, assuming it's not moving. The motion part, will come to it later. But let's assume it's not moving. You're just sitting there on an inclined plane. Okay, instead of saying, let's say you are sitting on a hill. Okay, you're just sitting there. You're not moving. Of course, the force of friction prevents you from sliding down. You see what I'm saying? But you're just sitting there, and you ask the question, what are the forces on my body? Okay. Now, before I do that, here is something. When when you draw the free body diagram, you always want to put the XY coordinates. And we are used to put the XY coordinate like that, you see what I'm saying? Right? X and Y. But for an inclined plane, you want to put the XY right on the surface of the incline. In other words, it's going to go like that. Now, you can do it this way. Oh, hold on. There we go. X and Y like that. In other words, the motion along the incline is the X, is the quote-unquote horizontal motion, if you will. Okay? And anything above is the Y, okay? You can do it this way, but it becomes a little bit harder. This is actually easier. It may sound weird, but it's actually easier, believe it or not. Okay, that's the first thing. So always, whenever you see an inclined plane, you want to put your coordinate or datums is along the incline, okay, where X is parallel to the inclined plane. All right, that's the first thing. Second, okay, what are the forces on it? Well, since it's just sitting there, you remember the book sitting on the surface of the table? What are the forces on it? Well, you get the mg, the weight, and the normal, correct? Well, we have the same thing. Now, why do we call the n normal? What is the meaning of the word normal? I talked to you about it last time. Normal means perpendicular. Okay, perpendicular to what? Perpendicular to the surface. Got that? This is very important. And the weight is pointing where? Downward? Well, downward where? Downward toward the center of the earth. Got that? This is important. So the weight always points toward the center of the earth, and the normal is always perpendicular to the surface. This is very important. You may want to write it down. Weight points to the center of the earth. Normal means perpendicular. To what? To the surface. To the surface. This is very important. All right. So what does that mean? Well, here is the block, or the child sitting on the playing a slide. So here is the weight of the child. It's down, directly down. There we go. That's the weight of the child, mg. Get that? And the normal, well, it is perpendicular to the surface. It's going to be like that. Watch. Along the y-axis. See that? See, there's the y-axis right here. That's the normal. So the normal is parallel to the y-axis right there. And the weight is toward the center of the earth. The center of the earth, way down there. Okay? So here we have an angle between them. See that? This angle is always the same as the angle of inclination right there. All right? You got to memorize that. Okay? You have to memorize that. Okay. Now we're set. This is the hardest part of the inclined plane. Second thing, now once I got that, I got those two vectors. This is the free body diagram that I'm going. Since this is the y, so the normal here is along the y-axis, and the x is this way, there are no forces on the x, but watch how the normal, the weight looks like. Well, it's kind of in between. It is not along the x-axis, and it's not along the y-axis. It's kind of in between. In other words, the mg here has two components, x and y component. You got that? Okay, so in this case, I have to resolve the mg into x and y components. Let me put a different color just to show you how that goes. I'll come back to pink. So what will happen is that the mg, and you can memorize those vectors, always the same every time. I'm trying to make it as neat as possible. Here it is. mg cosine theta, and down the inclined plane the mg sine theta. As a matter of fact, it's always the case. Sine theta, like that. So once I get those, then I can ignore this mg because it has been replaced by those two components. You got that, guys? And now when I ask the question, what are the forces along the x-axis? Go back to black. What are the forces in the x direction? Let's say sigma f sub x equals 0. Well, what are the forces along the x-axis? Well, we have the mg sine theta going this way, which makes it negative, right? See, here's my datum right there. That's the negative side of it. So that's mg sine theta, the negative. And then I have the sigma f sub y equals 0, and I have two of them, normal minus. And notice that we've always said that the normal is equal to mg here. Well, here on the inclined plane is actually the normal is equal to not mg, but mg cosine theta. Got it? Okay, more on that later. I'm going to stop here about the inclined plane, and what I have just said is directly related to the example that in the book, example 3. So let's go into it. I hope it's going to be easy now after reviewing all of that. So now we come to example 5.3. So go back to the picture. So the picture says, the only thing I want to is, okay, the angle is 26 degrees, and the weight of the car, see, remember, it's not the mass of the car. He gives me the weight of the car, 1.76 times 10 to the 4. Okay. So here is the, ignore the vectors. We're going to talk about them in a sec. So here is the car on an inclined plane. I have exactly the same situation I have just explained. So here is my inclined plane for the car. And here is the car. Let's make it a real car. How about that? I can draw a car. A classic 1940s car. There we go. There we go. Okay. And so what's going on here? Well, he said that the car is being pulled like that. See the chain? Right there. Okay. So it's being pulled by the tension T. So this is, I'm going to call it T, the tension. Okay. And of course, I have the weight of the car, mg, down, directly down, always vertical and downward. So that's the mg of the car. And then I have the normal, which is perpendicular to the surface, just like that. And that's exactly how we did it, actually. Look at that. So you get the normal, he calls it small n. And we got the same thing, right? Okay. And of course, I have the, the angle of inclination. He's calling it alpha. All right, let's call it alpha. All right. Now, I'm going to resolve. Resolve what? Well, first of all, here is my x and y. I'll put it here in the back. Oops. Here is the x and y right there. This is x, and this is y. Okay? So the tension is along the x-axis, so I'm not going to do anything with it. It's fine. There is no resolution of vectors. The normal is along the y-axis. I'm not going to do anything with it as well. The mg is the troublemaker, so I have to resolve it into the component, just like I did right here, right there. I'm going to do exactly what I've done right there. Okay? So here is the angle. Did I change the color? I forgot. Nope, I didn't. Should I change the color? Sure. Let's make it red. All right. So here I have, remember this angle is alpha. So it's going to be, mg cosine alpha. And then I have here mg, like this, sine alpha. Alpha, right. There we go. Okay? That's it. Now I can ignore this mg right here. See what I'm saying? I can ignore it because it's been replaced with those two vectors. And now all I need to do is apply Newton's second law for that. Let's do it. All right. So, oops, I forgot to change the color. I only like to draw with black because it's very clear. Even when I'm teaching the courses, face to face, I just use the black markers. All right, so we have sigma fx equal 0. Why 0, guys? Well, it's not moving. He said the car is at rest, so it's 0. All right, what do we have in the 0? The x component. Well, I got the mg sine alpha in the negative, and I got the tension in the positive there. So there we go. So I have minus mg sine alpha plus the tension equals 0. Done. Now let's do sigma f in the y direction equals 0. And that's, I have two of them. I got the normal right there and the up positive and then down mg cosine. So I'm going to do that. So that's going to give me normal minus mg cosine alpha equals 0. Okay? And he wants, I forgot what he wants. He says, find the tension in the cable. All right, T. Okay. I think we have everything. This, I can find the normal with this one, but he's not asking for it. I can find the tension. Let's find the tension. So from this equation right here, the tension in this case is going to be equal to mg sine alpha. And I believe I have everything. The mg is the weight of the car. He gives me the whole mg. He said it's equal to 1.76 times 10 to the 4th. So I can just plug it in. So that's going to be 1.76 times 10 to the 4th times sine, what's the angle? 26 degrees. And then I would just plug it in and I would calculate that. I hope you're calculating things with me. So that's going to be 1.76 E4 times sine 26, answer 7715.3. So I have here 7715.3 Newton. There we go. There is the tension in the chain. You see what I'm saying? Okay. Okay, let's say is he asking for the normal? I forgot. We can calculate that. Find the tension in the cable and the force with which the ram pushes on the car's tires. There we go. Look at that. And the force with which the ramp pushes on the car. What is he asking for? Well, he's asking for the normal. The normal is the reaction to the weight. So how much force the ramp is pushing, which is basically the normal vector. All right. And I have it ready. It's right there. So it's basically the normal is equal to mg cosine alpha. So that will be 1.76 times 10 to the 4th times cosine 26. And when I calculate that, so I have here answer 15818.8 Newton normal. And there we go. Got it? This is basically the reaction to the weight, if you will, right? And this is the tension, of course. Okay? All right, good. Now we come to, let me see if there is any other problem I'll work on before I move. Okay, now we come to the second law, where what if the subject or the object is in motion, is in accelerated motion? Let's do that. What if the object is in accelerated motion? In other words, the kinetic reaction, MA, does not equal 0. In other words, the acceleration does not equal 0. That's what I'm trying to say. You see what I'm saying? What if we have something like that? And so let me start with example. I just looked at it. Oh, yes. Example 5.5, page 128. Let me show you that. 128. Okay. Right there. Okay. So what you have in here, let me explain it to you. You know, when you have some, you have something hanging from your mirror. Okay. And let's say that you are on a red light. You're driving your car. You are at rest in front of a red light. And let's say you have something, say a cross or a necklace and a cross or something in your mirror. And then the red light turns green, and then you push on the accelerator, the gas pedal, and then you move forward. What will happen to that chain hanging from the mirror? It's going to move forward, right? Not forward, backward, right? It's going to move towards you. It's like that. Here it is, right there. See that? So the story here, basically, you have something hanging, a key, okay? And so the car moves forward when you push on the gas. The car moves forward. As a result of that, this thing moves backward like that, okay? Let me read that for you. He says, you tape one end of a piece of a string to the ceiling light of your car and hang a key with mass M on the other end. A protractor taped, so you want to measure the angle here. A protractor taped to the light allows you to measure the angle the string's base with the vertical. Your friend drives the car while you make the measurement. When the car has a constant acceleration with magnitude A toward the right, the string hangs at rest, making an angle beta with the vertical. He said derive an expression for the acceleration A in terms of the mass M and the angle beta in particular, and so on. I'm sorry, this is not F equals MA. I think it is just F equal the sum of the forces. Because we have an acceleration, yes, but he's not given any numbers, yes. Okay, so let's solve this problem. Let me explain that to you. So we have here let's say so here is the ceiling, if you will, right? And you are moving forward, so you get that thing, the key, whatever, is going inclined like that. Here it is. I'm going to turn it into a block again, just like that. And there is an angle here. He's calling it beta. And I forgot the data here, sorry. The rest is making an angle theta. Okay, the mass of it, the mass of the key is m, and then we'll put the numbers later. All right, derive an expression, okay? So we have the mass of the key is m. All right, how do we do this problem? Here is how we do it. I'm going to draw that. I'm going to draw what I have just done here in a free body diagram. Basically what that means, I'm going to draw the same thing, but I'm going to put the forces on it. Well, before we do that, let's have some quick thoughts here. What are the forces on it? First of all, there is no normal because the mass is not pushing against a surface. It's hanging, just like the chandelier. You see what I'm saying? It also is hanging in the air. So, but however, there is a tension in the string. You see what I'm saying? So it got weight and tension. That's it. There is nothing else. I can't think of anything else. Okay? All right. So what I have in here is my my key. I'm going to call it a block. So here is the weight mg, right? And then you have the tension. Remember, tension comes out of the body, and the tension is going this way. Look. There it is. Along this string. You see what I'm saying? There it is. And the angle beta is right here, right? So far, so good. There we go. And of course, the whole system is moving with acceleration a. Now, don't put the acceleration a with the block, okay? Just leave it outside because it's not a force. It's a kinematic variable. So just put it there just to remind yourself that this thing is accelerating. It's not in a static situation. All right. Before we do anything, you have to resolve vectors into x and y component. In other words, I have here sigma f as a vector equal to the null vector. I'm sorry, this is a ma. Sorry about that. So it's going to be ma as a vector. But then I'm going to resolve it into two components. Sigma f in the x direction equals ma in the x direction. I'm going to leave some space. Sigma f in the y direction equals ma in the y direction. You got that? Okay. Now, look at the motion here, guys. The motion is in this direction. And, of course, here's my datum, x and y. And the motion, as you can see, is in the x direction. There is no motion in the y direction. What does that mean? It means the acceleration in the y direction, or the y component of the acceleration, is really zero. Do you see what I'm saying? I mean, it's obvious, right? I mean, this whole thing is moving along the x-axis. So, as a matter of fact, let me just give you a little tip here. In our course, you will, I can't even remember one problem where the acceleration, the x and y are non-zero, okay? One of them have to be zero, you see what I'm saying? So, as you can see here, I hope you can see it, that motion in the y direction is equal to 0. So basically, sigma fy is simpler. There is no motion there in the y direction. Where the motion, the interesting stuff is happening in the x direction. All right. Now, before I plug in my variables there, I want to resolve the tension because it is not along the y and it's not along the x. I'm going to resolve it. So again, let me use a different color. So in this case, I have t sine beta, right? And t cosine beta. Is that right? You remember the angle here with respect to the y-axis, not the x, so you put the opposite, sine and cosine. You see what I'm saying? If you're confused about that. All right. There we go. And then I can ignore the big T here, and I'm just going to be dealing with its component, t sine and t cosine, x and y. Okay? All right. So, if I go back to sigma fx equals ax basically the acceleration a, the one that he's given me. So what are the forces in the x direction? Well, as a matter of fact, there's only one. This one right there. That's it. There's nothing else there. So that's going to be t sine beta equals ma. There we go. I'm going to box it. I'll come back to it in a minute. Okay? Now, in the y direction, I got two of them right there. This one and this one. Up, positive, down, negative. So that's going to be t cosine beta minus mg equals 0. This immediately tells me that the tension cosine beta is equal to mg, equal to the weight, or the tension is actually equal to mg over cosine beta. There we go. I have an expression for the tension, even though he didn't give me any numbers, but I do have an expression for it. In other words, if you tell me the mass of this key is so and so, and the angle is so and so with the protractor, I can actually get a value for that tension. You see what I'm saying? So there it is. And he also gives me the value of A. He said it's equal to A, any number, whatever it is. And I forgot what he wants. Hold on, sorry. Derive an expression for the acceleration in terms of the mass and the angle. In other words, eliminate the tension. All right, that's cool. Here is how we do it. We use the method, go back to your algebra. He basically finds what is A in terms of the angle beta and the mass m. In other words, eliminate T. How do I do that? Well, one way to do it, I can take T is equal to mg over cosine beta, right? I can take that, and I use the method of substitution, and I'll plug it right in here. See what I'm saying? So let me go back. Let me call this equation 1, equation 2. So I go subs 2 into 1. Is that all right? Let's do that. So when I do that, I'm going to write 1. So I'm going to replace T for that. So that's going to be mg over cosine beta times sine beta, you follow me, equals ma. Okay? The masses cancel out. And as you know, sine beta over cosine beta is tangent beta. So therefore, A is equal to G times tangent beta. And there we go. In other words, the mass cancels out, and that's basically an expression for the acceleration. Let me check how he did it. So this is his FBD, his free body diagram. Maybe next page. And there we go. He has the same thing. So A sub x, he still calls it A sub x, is equal to G sine tangent beta. Got it? Okay. Part B is simple. He says, you just basically plug in the value. He said in part B, in particular, what is A, the acceleration if beta is 45 and when beta is 0? Let's see. Okay. In other words, if you are really accelerating 45, that makes it really accelerating. You are really pushing hard on the gas pedal. 45 degrees, so we can just plug it in. Tangent 45, which is equal to 1 times 9.8, so your acceleration is 9.8, and 0, and so on. You get 0, so there's no acceleration, and so on. Okay, that's simple. You can just plug it in and get the answer. Okay, good. Next, here's another inclined plane problem. Example. I still have 2 more examples, or at least 2. Sorry, 1 second. Yeah, 2 more examples, and then we'll start doing problems. I still want to talk about the friction. That's another force. Anyway, I'm going to do example 5.6. That's on page 129. So here we go. We have an inclined plane problem. Same thing. The only difference is that those guys are actually in motion. Okay, it's not in a static situation. So we do exactly the same thing, except that sum of the forces is not equal to 0, but ma. Got it? Along the x direction. All right. He says, suppose a toboggan. I don't know what that means. Toboggan. Oh, okay. That's a little slide there. It's called a toboggan. I'm sorry, never heard of it. Toboggan loaded with vacationing students, total weight W. That's the total weight of the toboggan and the students. Slides down a long snow-covered slope. The hill slopes at a constant angle alpha right there, and the toboggan is well waxed that there is virtually no friction. Okay, we're just going to assume it's frictionless surface. Okay, that's basically what he's saying. All right, find the toboggan's acceleration, A. Okay, he wants to know A. And the normal force, okay? All right. Easy enough, I hope. Again, there's no numbers. I'm sorry, there's no numbers. But that's okay. So what I have in here is the following. Here's a picture. So it looks something like that. Incline plane. Always draw the free body diagram or the picture. It really helps you. Trust me. So I don't need to draw people on a toboggan. I'm just going to draw a block. How about that? It's kind of boring, but that should do it. There we go. And the block is sliding down. The angle of inclination is alpha. And then we ask the question, what are the forces on the block? We already talked about that. So we have here the normal, which is perpendicular to the surface. And I got the weight of those guys down toward the earth right there. You see what I'm saying? And nothing else really. Again, to remind myself, my x and y are going to be like that, my datum, okay? And then I would resolve the vectors. So the mg here, I'm going to do it a little bit fast because we've already gone through it. So the mg here is going to go, there is the y component down this way, and then the x component down this way. So here I'm going to have two vectors like that, where this one is mg, again, this is the angle alpha. So that's mg sine alpha. Sorry, there is a, hold on, let me erase that, I'll come back to it. There we go. So I have mg sine alpha. Here is, I'll put the datum here, how about that? Okay, and then I have here the mg cosine alpha, right? There we go. That's it. So what is the motion, guys? It's along the x-axis this way, A. In other words, this is A sub x, and A sub y is this way, but A sub y is what? 0. Those guys are not going up and down. You see what I'm saying? They're not moving up and down. They're moving, sliding down, sliding along the x-axis, if you will. But they're not moving. There is no motion for those guys in the y direction. You got that? So obviously the AY is 0. Okay? All right. So now I'm going to put in my, so I have here sigma F in the y direction is equal to 0, right? There's no MA. AY is 0, so it's just 0. Okay. And I'll leave a little space here. Sigma F sub x, which is the interesting one, because this is where the motion is taking place, is MA sub x. I'm just going to call it MA, okay? You can call it x there, but I'll just call it MA. All right. So what is F sub y? Well, F sub y, I get two vectors here. Normal minus mg cosine theta. So that's going to be normal equal mg cosine alpha, that is, right? And I just move the cosine, just solve for it. So basically the normal is equal to mg cosine alpha. Okay? Now along the x-axis, I'm going to have here, oops, let me go there. So I have here only one vector right there, and it's in the positive x direction. So that's going to be plus mg sine alpha equals ma. There we go. See what I'm saying? And he wants, so the masses cancel out, and so the acceleration is equal to g sine alpha. In other words, if he gives me the alpha, I can tell you what the acceleration is. I already know what g is, 9.8, so I can find it. And that's really what he wanted, isn't he? Yeah, that's it. So he said, what is the acceleration and the normal? There it is right there. Let's go back to the question very quickly. He says, find the acceleration. Oh, there it is. It's g sine alpha. And what is the normal vector? Well, here it is. mg cosine alpha. That's it. Okay, simple? Okay. All right, the next topic that I want to talk about is just a continuation of that, and that is the friction force. So let me talk about that before we take up more problems. Friction. What is friction? Friction is a force that opposes the motion. Okay? Now, when you ask the question, what is the direction of the friction force? It's simple. Look at the motion of the object. If it's moving to the right, the friction force to the left. If it's moving up, the friction force is down. If it's moving down, the friction force is up. It's really that simple. Always just make it opposite of the motion. Run the film in your head. You know, if you are looking at an object in a book, you're not seeing the motion of the object, because just a picture. But to run that picture as a film in your head and see where is it going. If it's going to the left, make it right. If it's going north, make it south, and so on. Okay, it always opposes the motion. This is the most important thing that I need to know. So the force, it's always, so if I have an object, let's say I have a car, and it's moving this way, the velocity, the friction force is going to be this way. Okay? If I have a rocket, and it's moving this way, okay, so the drag is called the drag coefficient. So the drag is going to be this way. The friction, by the way, the symbol of friction is small letter f for friction, okay? So that's the motion of the rocket, and so on. You got it? Okay. Now, the friction is equal to, okay, again, the small letter f is the friction, is equal to mu times n. N is the normal, okay? That's the formula for the friction. You need to memorize this formula. Okay, what is mu here? Mu is a Greek letter, mu, M-mu. And the way you write it, if you can't write it this way, you write a U and give it a little tail like that. See that? U and a tail. Okay, it's called mu. And the mu is called the coefficient of friction. Okay? Now, I'm not sure if you're taking a lab this semester, but there are at least one experiment that you'll be doing where you have to calculate the value of mu. Okay, so what is mu here? Mu, or the coefficient of friction, this is just a fancy term. The mu is always between 0 and 1. Okay, always between 0 and 1. And maybe I don't even need to put the equal sign there. Okay. If the mu is equal to 0, that means the surface is absolutely smooth. I'm talking extreme, so smooth there is no friction, frictionless. Okay? That's 0. 1, however, it is so rough, it's like there is a super glue on it. Okay? So this is 100% rough. Both situations are not physical, okay? They don't make sense in our real world, okay? But that's what you need to know. So if it's 0, it is absolutely smooth surface. You know, black ice, let's say you're sliding on a black ice, you know, in Minnesota, whatever, maybe that come close to 0. It's not 0, quite 0, but it's come close to it. 1, imagine, you know, let's say you have super glue on that object. You could hammer it all day trying to make it move with just one budge. Okay, that's just 100% rough surface. Got it? Okay. So in the real world, however, it's somewhere in between. For example, the street that you drive on, the mu value of it is somewhere 0.83 or something like that. Okay. The surface of your table, if your table is smooth, you know, somewhere, say 0.48 or something like that, and so on. It's always point something, okay? Point a number. Never 1.2 or 1.3. Never. If you get something like that, there's something wrong with your measurement, okay? Never. So it's somewhere between 0 and 1. And it's always positive, and it's not, doesn't have units, okay? It's just a coefficient, just a number. Okay, in other words, think of it like this mu, think of it like let's say if it's 0.3, let's say it's 0.3, which is a relatively smooth surface. So the friction in this case will be 0.3 times the normal, right? Something like 30% of the normal. Okay, so it's always a fraction of the normal, if you will. Okay, that's all you need to know about the friction. All right, and friction, the coefficient here, there are 2 types. There is one friction that is called mu sub s and mu sub k. This is called a static friction. And the k here is kinetic friction. Kinetic coefficient of friction. Kinetic coefficient of friction. Okay? So this one, and mu sub s, is the static coefficient of friction. M sub k is the kinetic coefficient of friction. What does that mean? Okay, what that means is the following. Let's say you have a box. let's say you have, let's say you have a big box and you want to drag the box somewhere. Okay, let's say you're pushing it. Let's say you have a sofa, okay, and you want to push the sofa from here to there. It's sitting on this wall, you want to move it to the other wall, okay? Have you noticed that when you are about to push the sofa, you will push harder until it moves, but once it gets moving, it's kind of easy to push. In other words, you don't exert as much force on it. Have you noticed that? Or if you have a car that doesn't work, I don't know if you ever pushed a car, it's always hard to get the car to move, but once it gets moving, it's actually easy to continue to keep it going. Okay? And the reason for that is because for an object that is in a static situation, is not moving, the friction here between the object and the surface, whatever it's sitting on, okay, when it's not moving, the coefficient is mu sub s. And this mu sub s is actually greater than mu sub k. But once this object gets moving, let's say now it's moving with velocity v, now the friction between the same surface, the same object, is mu sub k. And this mu sub k is smaller value. In other words, if mu sub s is, let's say, 0.48, once that object gets going, now it'd be 0.43, for example. I'm guessing a number or whatever, okay? It drops down, okay? And the lab experiment that you are working on, I'm not sure if you're doing lab this semester, but is you actually calculate the coefficient of static friction and the kinetic friction for the same object, and you prove that the static friction is actually greater than the kinetic friction. All right? Okay. So we go back. So we have here the friction force is equal to mu n, and then we say that mu F sub s, or kinetic mu sub k. And depending on the problem, I'm going to show you in a minute how that works. Okay? But keep that in mind. All right. Trying to find a problem. Which problem did I work on here? Oh, okay. Example 5.8. Let's do that. 5. Oh, okay, there it is. Page 135. There we go. So you got this guy who's pushing on this box, refrigerator, whatever. He's pulling on it this way, okay? Okay, let's read the problem. He says, suppose that the delivery company has just unloaded a 500 Newton, again, that's a weight, not a mass, crate full of home exercise equipment in your level driveway, all right? You find that to get it started moving towards your garage, you have to pull with a horizontal force of magnitude 230. So in order, you have to pull it, with 230 in order to get it moving. But once it gets moving, you don't require as much force. So once the crate breaks loose, okay, and starts to move, you can keep it moving at a constant velocity. Okay, what does that mean? I'll come back to it. With only 200 Newton force. See that? So because why you don't need the 230 anymore? Because when it's an object moving and it's sliding, the coefficient of friction drops down. The amount of friction drops, the roughness of the surface between them. The rubbing, okay, drops down. That's basically the meaning of it. Okay? So now he's asking, what are the coefficients of static and kinetic friction? Okay? Cool problem. All right, how do we do it? Let's see. 5.8. So what I have in here, first I'm going to draw the diagram. So here is the box that we're dealing with. And then always put all the forces on it. Well, he said it has a weight, mg, and of course it has a normal. Okay? Whenever you deal with friction, you better know what the normal is, or you need to deal with it, because friction is equal to mu n, so the normal is always significant. You get that? So keep that in mind. All right. And then now you're pushing on it with a force F, and this force is two kinds. One when it is in a static situation, 230, and then when it's dynamic situation or kinetic situation, 200. Okay, so you got two F's here. You got that? So you're trying to push it to get it to move, so that's 230. Once it gets moving, you only need to keep going with 200. Okay, I hope you understand that. So I'm going to call it F for now to apply for both situations. What else do we have? Well, what is the direction of the motion? Run the film in your head. Well, there it is. The direction of motion is this way, right? So the friction is going to be this way. And I always like to put the vector of friction close to the surface, you see what I'm saying? Just to remind you that's the friction force. And there we go. These are the forces on the object. You see what I'm saying? Now, one more thing he said. He said, you can keep it moving at constant velocity. What does that mean? No acceleration. In other words, it is sigma f equals 0 for both y and x. So here, my equations, sigma f in the x direction equals 0, sigma f in the y direction equals 0. Why? Constant velocity. That's the first thing. Okay? All right. To put the surface there, probably helpful. There we go. Okay. So how do we do it, guys? Let's start with, of course, the interesting part is that the motion along the x-axis. So let's start with that. So sigma f sub x equals 0. What do I have? I have minus f, the friction, plus big F, okay, the one that is 230 and 200. I'll come back to it, equal to 0. Done. Okay? Now let's do sigma fy equals 0 again. And as you can see here, I got the normal and I got the mg. So that's going to be n minus mg equals to 0. In this case, the normal is equal to mg, which is something I already know, especially if it's not an inclined plane. Most of the time, the normal is equal to the weight. There we go. Okay, so it's going to come useful in a minute, but that's what I have. Now, he said, go back to the problem. He wants the coefficient of friction in a static and kinetic situation. Well, let's start with a static. So here's my EOM, my equation of motion. Okay, but let's start with a static situation, which means what? While you are trying to push it to get it to move, in this case, the force F is 230, and the friction is actually a static friction. Got it? So this equation right here, guys, is we're gonna use this equation, number one, to apply for the static situation. It's gonna be minus F sub s plus F, big F, let's call it F sub s, how about that, equals 0, and that makes it minus mu s normal plus 230 equal 0. You follow me? You can pause the video and think about it. Now, remember, he's asking for mu sub s. Well, the problem becomes trivial. I already know what n is. It's right there. And he tells me the mass of, the weight, he said 500 Newton. So in this case, I can go back here and plug it in. So that's going to be minus mu sub s mg plus 230 equals 0. Solve for mu sub s, if I just do the algebra, 230 over mg, and there we go, I'm done. So it's 230 over mg, he said is 500, I think. 500 Newton right there, right? So that's going to be 500. So mu sub s, use my calculator. So I have here 230 divided by 500, answer 0.46. It better be less than 1. 0.46. Again, no unit. Okay, guys? No unit. This is a unitless, dimensionless number. There we go. All right, that's fine. So this is the static situation. Let's go to the kinetic. Motion-wise, if you will. So I'm going to use exactly the same equation right here, except now it's kinetic. So in this case, this equation 1 is going to be, well, let me remind you, F is equal to 200 Newton. Oops, I forgot to put the unit here, Newton. And then, of course, the F here is the kinetic friction, okay? So, again, I'm going to do the same thing. So it's going to be minus F. Again, I'm using this equation. Plug it in here. So minus F sub K plus big F sub K equals 0. And plug it in. So I'm going to have minus mu sub K n plus 200 equals 0 minus mu sub K, excuse me. And n is, we already got it. It's right here, guys, right? Which is 500. So that's going to be times 500 plus 200 equals 0. And therefore, mu sub K is equal to 200 over 500, and it better be less than 0.46, otherwise we've done something wrong. Remember, a mu sub s is always less than mu sub k, okay? So when I plug it in, so I have here 200 divided by 500, answer 0.4. So in this case, mu sub k is equal to 0.4. And there we go. Got it? Okay. Next. Oh, okay. I'm done with the examples. Oh, there is one more topic. That is, I mean, we're gonna come back to it. I'm just gonna go over it very, very quickly. That's he kind of covers it superficially, really, because we're gonna go back. We're gonna study that topic in details later. That's in section 5.4. Let me go over it very, very quickly. I only have one homework problem, very small, easy problem on it. Problem 45. It's a simple problem, level 1. So let me go over it very quickly, and that is Hooke's law. And then we'll be ready to do. I'll do at least a couple of problems from the homework. Again, this is section here. Let me show it to you in the book, page 139. Elastic forces, he calls it, okay? And he just I think a page and a half or something like that. Yeah, actually just one page, the rest are examples. Just one page, this page, that's it. It's called basically Hooke's law. I'm trying to find that Hooke's law. Should be mentioned somewhere here. H-O-O-K. There we go, Hooke's law right there, Robert Hooke. He was actually a friend of Isaac Newton. They knew each other. Anyway, it's a simple law. I write it differently from here. But anyway, what is it? Hooke's law. If you have a spring, let's say this is a wall, okay? Let's say this is a wall, this is the floor, and let's say I nail a spring to the wall like that. And the spring is just sitting on the floor, relaxed. It's unstretched, just, let's say a slinky or something. Okay, and now imagine that I would grab the side of the spring like this, excuse me, and then I would pull it. Okay, I would pull it with a force. Okay, so what's going to happen? The spring is going to stretch. Let's assume it's going to stretch all the way here. Okay, so it stretches all the way here now. So you have the new spring. Let me put it in a different color. How about green? So now the spring is going to stretch all the way here, okay? So what happens here is we call that, so remember, you started here. There's the spring. I always get them confused. We have the spring is right here, right? Where the stretch is 0. You see what I'm saying? X equals 0. When you say X here, we mean the stretch. Or the compression. For this matter, we're doing stretching. Okay? And then I stretch it from here all the way to here, to some X value, okay? So this distance, we call it the displacement of the spring. Displacement of the spring, okay? All right. And it turned out that the force that I'm using to stretch it, when I hold it with my fingers and I pull it, that force that I'm pulling it with is proportional to the displacement, which kind of makes sense. The more you push it, or the harder you stretch it, the more displacement you get. Kind of simple, right? Even for compression, the more you compress the spring, the more compression displacement that you get in the negative direction. So that's basically what the law says. So if F is proportional to the displacement, then F is equal to a constant multiplied by the displacement. Make sense? And this constant, we call it small letter k, so F is equal to kx. I don't know if he put the minus there or not. No, he didn't put it, because technically you should put a minus there, but we're not going to do it now until we cover it later. So anyway, that's basically Hooke's law. What is k here? Well, it's called in the book, and most likely if you take this course with if you've taken it with your high school teacher, he called the spring constant. And I don't like this term at all. Okay, it's the best term for it is the stiffness constant. Learn this word, the stiffness. The stiffness constant. What does that mean? Well, let's go back to our example here. So I'm starting with a spring that is unstretched, correct? And then I pull. I exert a force on it by pulling it to stretch it. Well, don't you agree with me that it really depends how stiff the spring is? You could have a slinky, which is really, you don't need a lot of force to stretch it. But if you have a stiffer one, you need more force to stretch it. You got that? So it all depends how stiff, how strong the spring is. And that stiffness is really what K is. Got it? So your book would call it the spring constant, which really doesn't describe it. I like the stiffness constant. So what is the unit of the stiffness? Well, let's look at the, as you can see here, if we look at the equation here, so you have F equals Kx. So K is force over X, the distance. So if I use it in terms of units, so a Newton per meter. See that? There it is. So this is the unit of the stiffness. I'll give an example. A slinky, the stiffness constant of a slinky, if I'm going to guess, it's probably 10 Newton per meter. Maybe less, maybe 9 or 8 Newton per meter. However, you know, you see that spring underneath your car, 4 wheels, you see them? You see that big, this big coiled spring under your car. That's about 20,000 Newton per meter, okay? So it depends on how stiff the spring is, this K value. Got it? Okay. I'm going to stop here as far as this is concerned. I am sure you can do that problem, the one I just told you about, number 45, without any issue. So anyway, let me go to the homework problem. I'm basically done with the chapter covering it. So let me do a couple of homework problems before we call it a day. And I have, oh yeah, I have number 5. Number 40, I think some of you are going to find it hard, so I'm going to do number 40. That's gonna, and maybe number 5. Okay, those are the 2 problems I'm going to work on. You're more than welcome to ask me or ask the professor if you want me to work on any other problem. I'll be more than happy to do that. So let me do number 5 and 40. Okay. On page 146. Right here, this one, number 5, okay? It's level 1. It's not a big deal. This one is also, this one is a homework problem for you. Kind of a little toughy. Similar to this one. Let me know if you get stuck on it. This one, I think number 9 is homework. I think, if I remember correctly. Okay, number 5. So here's the picture. You got this guy hanging from a string like that. He says an adventurous archaeologist crosses between 2 rock cliffs by slowly going hand over hand along a rope stretched between the cliffs. Okay, like Rambo or whatever. He stops at rest at the middle of the rope, right there. The rope will break if the tension exceeds 2.5 times 10 to the 4 Newton. Okay, so that's the maximum tension the rope can withstand. Our hero's mass is only 90 kilogram. All right. A. If the angle theta is 10 degrees, what is the tension? That's the first question. Start with the B. Okay. B. What is the smallest value of the angle theta can have if the rope is not to break? Okay? All right. How do we do this problem? Again, I'm going to draw it. So it's going to look something like that. I mean, I'm exaggerating how the angle looks like, but that's okay. There we go. It's not even, is it? Let me do it one more time. Take this out. Sorry, I'm a little perfectionist. Let me do it better here. There we go. I think this is better. All right. So this is the angle theta. I'll come back to the value in a minute. And then we have the archaeologist. I'm going to turn him into a block right there. Okay? There we go. And now we ask the question, what are the forces in the system? Well, you get the weight of the archaeologist. And as you can see, the problem is highly symmetrical, which means the tension in the rope here, the tension in the rope here will be the same, because he said right in the middle. If it wasn't in the middle, it would be two different tensions, you see what I'm saying? And those are the same angles. So everything is symmetric. It's an easy problem. So in that case, so I'm going to call that T right there. And this one, T, I don't need to call them T1 and T2 because they're equal. Just like that. And that's it, really. There is nothing else. There is no normal because there is no surface to push against. So that's basically what it is. Now let me draw the FBD, the free body diagram. So I'm going to draw the block, or maybe make a point right there, this point, whatever, however you want to do it. So I'll just make it a block like that. So I got the MG, and then I got two of them. And remember, this angle right here, guys, is theta, right? And this one is theta. I hope you believe that. So now I'm going to resolve. So it's going to be T cosine theta, T sine theta, and then for the next one, I'll make it a big dot. Then I have also T sine theta, and then this one is T cosine theta. You can pause the video and think about what I've done, and I hope this is clear for you. Now, what do you notice here? What you notice is that the x components will cancel each other out. They're equal, and they're opposite. So basically, I don't need the x components at all. See that? So the only interesting vectors here, or forces, are along the y-axis. See what I'm saying? Let me put in the numbers there. So he said before I do the problem. So I have tension, he said, is 2.5. I'm copying it from my hard copy. 2.5 times 10 to the 4th Newton. That's, oh, this is the maximum tension, sorry. I'll come back to it. And then he said the mass of the guy is 90 kilogram. That's about, what, 190 or something like that? A pound. And then now for part A, he said theta is equal to 10 degrees. Okay? And he wants the tension, if I remember correctly. If the angle, yeah, find the tension. Okay? So this is the FBD right here, guys. Okay? So let's find the tension. Well, as you can see, if I put my datum, I don't need to put it. But there it is. This is X and Y. There's nothing in the X direction. It's all in the Y, right? So this is minus Y. So we have here sigma F in the Y direction equals 0. It's a static situation. There's nothing moving, right? He's not falling down or whatever. So in this case, I'm going to have T sine theta plus T sine theta minus mg equals 0. There we go. That's it. So that's equal to 2t sine theta minus mg equals 0. Now I can solve for t. He wants the tension, so I can do it in one shot. mg over 2 sine theta. There we go. I have an expression for it. Done. You just plug in the numbers, right? So what is the mass? 90 kilogram, 9.8 divided by 2 times sine 10. And then you just calculate that. I'm going to have you do it. And there we go. We're done with the problem. Easy? I hope so. All right. Part B. He said, what is the smallest value of theta? Basically, he's asking for theta if the tension is max. See, he said, what's the smallest value of angle theta can have if the rope is not to break? In other words, if he is pulling on it with the maximum tension, what would be the corresponding angle? You see what I'm saying? In other words, I am going to use the same formula, except that I'm going to put, I'm going to put the tension to be the Tmax, this one, right there, and then I'm going to find out what is the corresponding theta. Simple. So I'm going to go back to the same equation right here. Here it is. But now it's kind of tailored or customized to my to this solution. So that's going to be Tmax is equal to mg over 2 sine theta min, if you will, minimum theta. You see what I'm saying? I don't need to put those subscript if it bothers you. But anyway, I'm going to solve for sine min. And that's equal, if I do the algebra, I can do it in my head, mg over 2t max. And all I need to do is just plug it in. So I have the mass is 90 times 9.8 divided by 2. T max, he gives it to me, is equal to 2.5 times 10 to the 4th. And then you just calculate that. Let's do it. I'm going to do it. So that's going to be so I have 90, times 9.8 divided by 2 divided by 2.5 to the power of 4 times 10 to the power of 4. Answer 0.0. I hope I did it right. 0.01764. So that's sine theta min, right? So therefore, theta min is sine inverse 0.01764. And that's, I just take the sine inverse of this number. Answer 1.01. 1.01 degrees. There we go. Okay, check my work. But that's how you do it. Got it? Okay, good. The last problem that I want to do is number 40. A little bit long, but it's not difficult. Okay, number 40. Page 149. This is 149. Right there. Okay, you see this right here? Okay, it says, it's a long problem, but it's not bad. It says a person pushes, okay, you got this box, okay? So the guy is pushing on it like that, in this direction, and 30 degrees below the horizontal. You see that? Okay, it says a person pushing on a stationary 125 Newton box with 75 Newton at 30 degrees below the horizontal, okay? The coefficient of static friction between the box and the horizontal floor is 0.8. That's static, which means the box is not moving. Sigma F equals 0. Cannot be MA. Okay? Make a free body diagram. Okay, we'll do that in a sec. What's the normal force on the box? What's the friction force on the box? What is the largest friction force could be? The person now replaces his push with 75 pull at 30 degrees above the horizontal. Find the normal force of the box. Okay? All right. Let's see how we do this. Since it's the last problem, I can drag it here. There we go. Okay, so what I have in here, guys, is this. Here is the box right there. Here's the surface. And the force, as you can see from the diagram on the side, is like that. And then the angle is right here. Or I can do it here. It really doesn't matter. Whichever you feel comfortable with. And then, of course, we got the mg is 125. He gives it to us. And this force, let's call it F. It's equal to 75 Newton. He said that in the problem. And he said, while the box is, this person is pushing on it, but he didn't move it yet, okay? So he's about to move it. So there is a static friction. And that static friction is always opposite the motion. Remember, he's moving it in, he is exerting a force this way, so you would think the box will move this way. Therefore, the friction is going to be this way. Get that? So there is the friction force right there. Oops. F sub S, just to remind myself. And then, of course, there is the normal. Whenever you put friction, think normal. Normal vector, that is. All right, there we go. These are the forces on it. Okay? He said draw the FBD. The FBD, basically, you put a point representing the box, and you just put all those forces on it. Okay? Hold on. Let me just do one more thing. So I'll come back to the FBD in a second. I want to resolve this vector, this force, into components, because the friction is along the x, and the weight and the normal along the y, everything no problem, but except this force is kind of crooked, so I want to resolve it. Again, let me change the color. Green. So there we go. So it's going to be one force this way and one force this way. This one is F. What is it? Sine 30. And this one is F cosine 30. You can pause the video and think about why I picked sine and cosine here. But it should be, let me make sure I did it correctly, minus sine, so that's going to be a cosine like that. Yeah, it should be sine, yes. There we go, okay? So now, if I'm going to draw the FBD, well, I'm just going to put those forces, all these forces on this knot, if you will, okay? So here I have the normal, right there. I have the friction right there. I have the mg like this. Whoops, should be vertical. I'll make this big dot like that so I have more space. There's my mg right there. And this is the F sine 30. And then this is the F cosine 30. And there we go. That's the FBD right there. FBD. Got it? Okay. Now we come to part B. This is part A. So part B, he says, what's the normal force on the box? All right. I'll just keep it here. Okay, so I'm not going to listen to what he's doing. Let me put in my equation in motion. So I have here sigma forces in the x direction equals 0. And then space sigma force in the y direction equals 0. Okay, what are the forces here in the x direction? I have two of them, right? I got two of them here. So the ones are friction minus F cosine 30 equals 0. And I'm pretty much done. As you can see here, I can actually find the friction force because I know what big F is, 75, and cosine 30 is 0.866. I can plug him in and I will get the answer. You see what I'm saying? I'll come back to it in a minute. So let me just box it and call it equation 1. I'll come back to it. For equation 2, or sigma F sub y equals 0, what are they, guys? I have three of them. We got the normal, the mg, and the f sine. You see that? So that's going to be n minus mg minus f sine 30. All of that equals 0. And then he said, what is the normal? Well, here it is. mg plus F sine 30. And guess what? I think I got everything. Here, plug it in. He said the mass, did he give us the mass? I hope he did. Yeah, he said the weight is 125, right? So mg is 125. So that's going to be 125 plus F is 75 times sine 30 is half. And then we just go 125 plus 75. How's half 75? 75 times 0.5. Answer 37.5. And that will give me 162.5 Newton. There we go. Simple? Okay. These are from the normal. All right. C. What's the friction force on the box? Well, here it is. Right there. I can find it from here. See that? So I can go back to equation 1 and just solve for small f. So here I have from equation 1, small f is equal to F cosine 30. Plug it in. So I have here 75 times cosine 30 is 0.866. So I have here 75 times 0.866. Answer 64.95. Shall we say just 65? There we go. Okay. Part D. What is the largest friction force? I'm sorry, I think I did that already. Did I? Oh, okay. What is the largest friction force could be? And I think it has to do with the static friction. So he said the coefficient of static friction between the box and this is, so the largest is really with a static friction 0.8, okay? You remember this friction here is somewhere, you know, it could be larger than that. This is not necessarily the largest one. So we know that the friction force, let's call it max, is equal to mu sub s times n. I already got the n for part B, remember? Right here, 162.5. So I have here, and the mu sub s, he gives it to me, 0.8 to 162.5. It should be larger than 65. That's just my prediction. Otherwise, it won't be max, right? 162.5 times 0.8. Answer 130 Newton. Okay? That's F max. Next, in part E, is that a part E? Yeah. He said the person now replaces his push with a 75, same force, pull at 30 degrees above the horizontal. Okay, the hardest part about this problem, I remember when I worked on it, is you need to draw it the correct way. There are several ways of drawing it where the pull is actually above the horizontal. Here is the correct way. Oh, sorry, what's the question? I forgot myself. Find the normal force in this case. Okay, in other words, see, let's go back to the old picture. Well, here's the old picture right here. See how the picture looks like? See that? So the force 75 below the horizontal. Okay, so I want to pull it above the horizontal, and the way it works is this way. Okay, it's kind of tricky. This way. In other words, if I'm going to draw it again, it's going to look like this. See, it's above the horizontal now. See, here is the horizontal. Now it's above it. Okay, that's the trick. And then we're going to do the same thing, except that rather than dealing with this kind of force, we're going to deal with this force, but everything else is there. So in other words, here is the mg, the good old mg. Here is the friction. And what else do we have? the free body diagram right there. We have, whoops, go back. There we go. There we go. I have the normal, so I just forgot to put the normal. So the normal is right here. I'll put it on the side, sorry, like that, okay? So now when I get my equation of motion, and I'm more interested in the normal, since it's normal in the y direction, so f sub y equals 0, that's going to be, well, okay, so let me resolve it, sorry. Let me use a different color. So as far as the force F is concerned, it has two components. One component like that, this is F sine 30, and then have another one right there, F cosine 30. See that, guys? And in this case, so now I'm going to go, if I want to do the normal, which means I'm going to be concentrating only on the y, excuse me, the y coordinates, that is. So I have how many of them? I got the normal vector right there, and I have the F sine right there, and I got the mg. That's it. So I'm going to write that down. So I'm going to have n. I'll put it above, below it. I don't want to clutter things here. So here I have sigma f in the y direction is 0. So in this case, I'm going to have the normal plus f sine 30 minus mg equals 0. And there we go. You just plug it in. Now take this, look at this one, this equation, and compare it to the old normal when the force was below the horizontal. It's right here, where normal minus mg minus f sine 30. Look at this one. It is minus mg plus f sine 30. That's the only difference, that it's plus rather than a minus. Okay. Anyway, we just plug it in. So the normal is equal to mg minus f sine 30. And then you just plug it in. So you have here 125 minus 75 times 0.5, and then 125 minus, what is it, 37.5, is that right? And then when you calculate that, 87.5 Newton for the normal. And there we go. We have the normal vector there. Okay? Next, find the normal. That's it. So, okay, that's it. I hope you have learned a lot from this lecture. Please let me know. Have a good week. Bye.